Look closely at a heavy, unstable atomic nucleus. To reach stability, it violently ejects a small cluster of 2 protons and 2 neutrons. This structural instability typically surfaces in elements with an atomic mass greater than 210. These massive nuclei shed weight through this precise mechanism, known as alpha decay. Classical mechanics dictates that this exact event is strictly impossible. Every particle inside the nucleus is confined by an immense boundary. To break free, a particle needs a specific minimum amount of escape energy. We can measure the actual kinetic energy of the alpha particle trapped inside. This chart compares a particle's kinetic energy against the required escape energy. The towering bar reveals a massive energy deficit. Under the rigid laws of classical physics, a particle cannot borrow energy it lacks. It is permanently walled in. Yet, if you place a Geiger counter near a block of uranium, you will register alpha decay happening continuously. To understand how the universe allows this, we must discard classical particle physics entirely and apply George Gamow's 1928 theory of quantum tunneling. The instability stems from the microscopic forces fighting inside the nucleus. Protons and neutrons are bound closely together by 3 femtometers, and the strong force drops to nearly 0. Competing directly force repels them from one another, trying to tear the nucleus apart. Unlike the short-range strong force, Coulombic repulsion has an infinite range. As you pack more nucleons into a growing atomic structure, the diameter of the nucleus expands. The strong force binding a proton remains strictly limited to its immediate neighbors. The repulsive force, however, compounds across every single proton in the entire structure. Eventually, the growing atomic nucleus reaches a critical tipping point where the total outward push overpowers the localized inward pull. At a specific size limit, Coulombic repulsion automatically dominates over the nuclear force. This physical limit dictates why we only see roughly 100 stable elements. Beyond this threshold, repulsion prevents a cohesive atomic structure from holding together. An atomic mass over 210 guarantees an inherent force imbalance. The massive nucleus must violently eject mass. We can map these opposing physical forces into an abstract energy landscape. This model depicts the boundary of the strong force as a square potential well. It forms steep energy walls that confine the nucleons. The repulsive Coulombic potential acts as the exterior of this barrier, represented by a declining curve falling away from the wall. The peak of this combined barrier requires an energy of roughly 20 to 25 mega-electron volts to cross. You can see this specific geometry verified in these notes, outlining the square well and the 25 mega-electron volt peak. But an alpha particle inside this well possesses a kinetic energy of only 4 to 10 mega-electron volts. The wall is roughly 2.5 times taller than the energy the particle has available. How does an alpha particle with 10 mega-electron volts come out of a well that demands 25? Gammow recognized that we have to stop treating the alpha particle as a solid physical object. Instead, it must be modeled as a wave function. Under wave mechanics, governed by the Schrödinger equation, the rules change entirely. The wave is constantly colliding with the boundary of the potential well. The wave function penetrates the wall, decaying exponentially as it travels through the barrier thickness. Because the nuclear barrier has a finite thickness, a severely attenuated fraction of that wave emerges on the other side. The particle retains a distinct mathematical probability of passing through the barrier, regardless of its kinetic energy deficit. This is quantum tunneling. Alpha decay occurs as a statistical leak of a wave function through a classically insurmountable barrier. We can scale this concept up from a single alpha particle to a macroscopic piece of radioactive material containing billions of atoms. For any individual nucleus, tunneling remains entirely unpredictable. We cannot know when a specific wave will breach the wall. We only know its exact probability of escape per given unit of time. Radioactivity is strictly probabilistic, derived directly from the randomness of the quantum state. But when you apply that static probability to billions of atoms simultaneously, the chaos averages out. Those erratic, individual quantum leaks form a highly predictable, smooth, exponential decay curve. This chart shows the mathematical decay of an isotope over time. Through a direct algebraic derivation, this exact curve yields the standard measurement we use in applied physics, the half-life. The decay constant, lambda, is just the macroscopic translation of Gamow's microscopic wave transmission probability. The reliable, predictable half-lives of the elements emerge from the collective behavior of wave functions breaching impossible barriers.